In this segment, I'm going to discuss climate change at the local level here in Boston, Massachusetts, and present some simple diagrams that demonstrate how tides, storm surges, and sea level rise interconnect. First, let's focus on the connection between global climate information that we've learned from organizations like the United Nations Intergovernmental Panel on Climate Change and how we're actually experiencing the warming of the ocean here in the Boston area. I'll provide this local perspective by looking at 3 recent news items that bring climate change home. In July of 2013, news outlets began to report that Entergy, the company that owns and operates the Pilgrim Nuclear Power Plant in Plymouth, Massachusetts, might need to shut the plant down because the cooling water for the plant is taken from Cape Cod Bay, was too warm to cool the plant safely at full operation. Ultimately, Entergy actually did not shut the plant down back in July, but plant operators did have to reduce production by 15 to 25% to cope with the increased water temperatures in the bay. This suggests that water today is warmer than the power plant's original design parameters. The next day, here on the UMass Boston campus, we got a memo saying, "Be careful, the rooms might not be as cool as you're used to." The reason for this is that UMass Boston uses water from Savin Hill Bay, and during the July of 2013, the water was too warm to fully support the needs of the air conditioning system to work at full efficiency. And in late September, the Cape Cod Times reported rising ocean temperatures draw diverse species to the northeast. The changes have already begun to occur, and we are now witnesses to these changes. We'll now turn our attention to sea level change. There are a number of processes that cause sea level rise or fall, as shown on this slide. Global processes include warming of the oceans, changes in ocean circulation, melting of glaciers and land ice. Local processes include subsidence and uplift of the land surface and storage of fresh water in reservoirs. Short-term changes in sea level can be caused by storm surges and tsunamis. And once or twice a day, the tides change the level of the sea. Next, let's look at a chart showing global sea level rise projections from the scientific literature. The higher end of the global sea level rise projections for the end of the century is 1.8 meters. That's about 6 feet of sea level rise. However, as you can see, there's a wide range of uncertainty with these predictions, and the uncertainty increases going forward into the future. Also shown on the right-hand side of this chart, for reference, are the projections for sea level rise from the 2013 IPCC report, which are more conservative. The higher end of the IPCC projections is approximately 80 centimeters, or 2.5 feet of sea level rise by the end of the century. Our approach to sea level rise is to look at the problem from an engineering perspective. We want to consider, at the worst case, plan around it, think about it, and then scale down our discussion to what's actually happening today. As I'll discuss in the next segment, this approach supports the prepare and monitor adaptation concept. The maps that you're going to see going forward are based on discrete values, 2.5 feet and 5 feet of sea level rise. Sea level rise of 2.5 feet, just about the middle of the graph, approximates the higher end of the projections for approximately mid-century. Sea level rise of 5 feet at the top of the graph approximates the higher end of the projections for the end of the century. In our research, we believe that these are plausible sea level rise scenarios that we might experience at some point in the future. Yet there are no probabilities or time frames associated with these scenarios. So what do these sea level rise projections mean for Boston? One problem with increases in daily tide heights is flooding of basements, sewers, and other low-lying areas, and additional flooding during bi-monthly and other astronomical high tides. And storm surges, which are key to this discussion, are going to reach further inland and flood areas that were not flooded before. As we record this presentation today, it's high tide here at Savin Hill Bay, and this diagram depicts a modern-day high tide in a hypothetical location, but it could be here, now. And this diagram depicts the same hypothetical location at low tide. The next diagram depicts what I like to hear phrased as wicked high tide. We think that phrase was coined by Bud Reese from the Boston Aquarium. We're not exactly sure who said it, but we latched onto it and we love it. A wicked high tide is a spring tide, also known as an astronomical high tide, which occurs twice a month during the full moon or the new moon. The Earth and moon are lined up and the tides are larger. It's a regular phenomenon. Now let's factor in sea level rise. Here we've got a diagram that depicts low tide with sea level rise. Here's high tide with sea level rise. This will be a good time to look back at the diagram of wicked high tide for a theoretical reference point, but the real reference point is Morrissey Boulevard, right over there. There's a low point in Morrissey Boulevard, over on the other side of Savin Hill Bay, that twice a month gets flooded with salt water. So now let's look at a diagram that shows wicked high tide with sea level rise. So you can see wicked high tide with sea level rise starts to push over the barriers and perhaps would include some flooding in the low-lying areas that now flood twice a month during wicked high tide. You're right on the edge, maybe over the top of the barriers if there were large enough waves. So now let's see what happens when we add storm surge to this diagram. And this diagram doesn't even accurately describe what happened in New York during Hurricane Sandy storm surge, where the tide was actually over the barriers because it was a much higher storm surge than this diagram shows. Conversely, when Hurricane Sandy storm surge came to Boston, it was low tide. It may have looked like high tide in Boston when the storm surge came in, but it was actually low tide and a storm surge. Imagine, though, what we'd have gotten if we'd had a storm surge at wicked high tide with sea level rise. At this point, we exceed our existing infrastructure. So in this presentation, I've covered sea level rise projections from the scientific literature, described our approach to sea level rise modeling, and discussed the interconnected concepts of tides, storm surges, and sea level rise. These concepts provide the basis for imagining adaptation and mitigation options we might need to make locally and globally to accommodate what the science indicates will come to pass at some point in our future.